In part A, we determine if A vector and B vector are parallel to each other. So we see that two vectors are parallel to each other if one vector is represented as a scalar multiple of another vector. Let's see if this could be worked out for these two vectors. I'm going to consider the B vector, that is negative 6. The components of B vector is negative 6, negative 18, and 3, and from this I'm going to factor out negative 3. So when I factor out negative 3, I should divide each of the components by negative 3, that is negative 6 divided by negative 3, and this equals a positive 2. So I put positive 2 here, and then the next component is negative 18 divided by negative 3, and this equals 6. So this one is 6, and then the last component is 3 divided by negative 3, and this equals negative 1. So here I put negative 1. Now we can clearly see that this is nothing but the A vector. So this equals, replace this vector by A vector, we get negative 3A vector. That is, we are now getting the relation B vector equals negative 3A vector. So we are able to see that the B vector is a scalar multiple. It's a scalar multiple of A vector. And so when we see that this vector is a scalar multiple of another vectors, the two vectors are parallel to each other. So therefore we see that A vector and B vector are parallel. There is also an alternate way to determine if A vector and B vector are parallel. So let's also understand the alternate way. For that, let's consider the two vectors, that is A vector, and this is given by the vector components 2, 6, negative 1, and then the B vector is given by the components negative 16, negative 18, 3. We see that these two vectors are parallel to each other when we see that the ratio of the corresponding vector components are the same. That is, we find the ratio of the x component, which is 2 divided by negative 6, and this equals negative one third. And we also find the ratio of the other y components, that is 6 divided by negative 18, and this equals negative 1 3. And also find the ratio of the z components, that is negative 1 divided by 3, and this equals negative one third. And so we are now able to see that the ratio of the vector components are negative 1 by 3, and they are the same. And this means that these two vectors are parallel. That is, A vector and B vector are parallel. This is the alternate way of determining that if two vectors are parallel to each other. In part B, we determine a unit vector that is parallel to A vector, and we can use the formula to determine the unit vector that is parallel to the A vector. And so this is given by the formula A vector divided by the magnitude of A vector. So first, let's find the magnitude of A vector. The magnitude of A vector is equals the square root of the sum of the squares of the corresponding vector components. So we take the square of 2, that is 2 square, and then we take the 6 square, add them. Then the last component is negative 1. We take the square of this one. We then have to take the square root. And so this gives 2 square is 4, plus 6 square is 36, plus negative 1 square is 1. And so adding this together inside the square root, we get 36 plus 4 is 40. 40 plus 1 is 41. Therefore, the square root of 41 is magnitude of A, which we now replace into the unit vector formula. So therefore, we say that unit vector that is parallel to A vector is this equals a vector. Replace a vector by the component vector form, that is 2, 6, negative 1, and this divided by the magnitude of a vector, which is under the root of 41. So this can be written by multiplying this 1 by root 41 into each of the corresponding components. So first we write this as 1 by root 41, which is the scalar, times the vector 2, 6, negative 1. And then we distribute this into all the vector components. So we finally write this as in vector form as 2 over root 41, comma 6 over root 41, and negative 1 over root 41. And so this is the unit vector that is parallel to a vector.